A very good morning to one and all present here for the day 2 webinar organized by Bharadasan University Entrepreneurship, Innovation and Career. Myself, Tyagarajan, working as Assistant Professor in Department of Computer Science, Central University of Tamil Nadu. And today's topic of discussion is on Internet of Things, that is IoT architecture. And this is a course overview for this 5 days webinar. And yesterday, that is on day 1, we have extensively looked and explored the topic introduction to Internet of Things. And today, it's a day 2, we're going to discuss in detail about this Internet of Things, that is IoT architecture. Tomorrow, we're going to discuss on IoT clouds, analytics, and visualization. Day 4, we're going to discuss on networking and internet in IoT. Day 5, we're going to discuss the current trends in Internet of Things. What are the current avenues that is open for the researcher to explore. These are the 5 webinar titles. Before we proceed into today's lecture, we will just do a small recap of day 1. Yesterday, we discussed what is an IoT. We said that the IoT is a device that should have a computational intelligence along with the network connectivity. Then we can say any device which is having the computational intelligence and network connectivity, we can call it as an IoT device. To better understand the IoT, we have given you some examples like a smart refrigerator, smart transport system, smart logistics, and smart home appliances, which we discussed in detail. Next, we also discussed what is an IoT and how it is different from the computer. IoT devices are very specific devices. They are designed and they are manufactured to do a very specific task. Whereas computers are a general purpose system. It can do any task, like it can do multiple number of tasks at the same time. Whereas IoT devices are designed only to do a very single task at a time. And what are the different trends that made this IoT possible? So we discussed so many trends that made IoT possible, and we also looked into the footprints of this IoT in all walks of life. That is, IoT is pervasive. We also discussed on that. We also discussed on the risk, privacy, and security issues that IoT brings us along with these advantages. Lastly, we have seen about IoT vision and the growth. As I said, today topic of discussion is on IoT architecture. Before we proceed into the architecture, we should know what is an embedded system. The embedded system, basically, it's a computer-based system, but they don't appear to be a computer. Is the definition slightly confusing? No, it's very clear actually. Embedded systems are computer-based system, but they don't appear as a computer in the sense the complexity of the embedded system is hidden from the user. Maybe you can say complexity is in abstract level. So the details of the complexity is hidden from the user. That's why it says embedded system is a computer-based system, but they don't appear as a computer. And embedded system is much more than the desktop and the laptop. So the figure which is given in the slide is a embedded picture, embedded system picture. So next we're going to see what is embedded system. So one such example is just that this digital camera is an embedded system. If you see the picture which is there in the slide, we can call this as an embedded system or an IoT device. It's a question for you. Please think for a second and tell me whether the picture which is portrayed there in the PPT, whether it's an embedded system or an IoT device. This is not an IoT device by arguing and putting a point that it does not have any network connectivity in it. And we can state this reason and we can declare that this is not an IoT device, whether it's a simple embedded device. And in general, embedded system will have a very simple user interface, user interface, since because embedded systems are focused on only one task, the UI will be very simple. For example, take this digital cam. This digital cam will have a click button and rewind button, backward rewind and forward rewind button. And the user interface is very simple. Whenever user want to take a photo, just click the button and the job is done. And as I said, this embedded system hides the complexity of the process. For example, if we take this camera, whenever user press the click button, it will capture the image, and it does a lot of image processing technique in it. Like we want to enhance the lightning mode of the image, or you want to take the see the image in the black and white format. Everything can be possible, and a huge number of image processing algorithm runs inside this digital camera. but this functionality, the complexity of the system has been hidden in the embedded system. That is very well appreciated by this example. And TV and cell phone are some of the embedded system examples. And the embedded system, like previous digital camera, we have seen that the embedded system directly, like digital camera, directly interacts with the user. It need not be the case at all times. There are some embedded systems that will not interact with the user directly. It needs an intermediate interface which facilitate the interaction of the user with the embedded system. For example, take this pen drive. User cannot directly interact with the pen drive. In fact, we need an intermediate. That is, we need a computer. This embedded system, like the USB disk which is shown in the slide, it has to be inserted inside the PC or the computer. Then in turn, the user will interact with the computer and it will do the operations on the pen drive. And another example we can give that this embedded system needs the interface for its interaction is that anti-locking braking system. So whenever user drives a car and whenever he wants to communicate with the braking system, he cannot do that directly. He needs an interface. That interface is nothing but the braking system. The brakes are the intermediate. The user has to communicate, or he has to give the force to the brake, and in turn the brakes will communicate with the braking system. So sometimes embedded system need an interface to enable the communication between the user and the embedded system. And efficacy rule. The most embedded products are mostly used on the critical market. Critical market in the sense, embedded systems are mostly used in the military and it is used in the healthcare domain. Considering the crucialness of these domains, the output that is from the embedded system should be of great accuracy. We cannot afford to have a point not error in this domain by the embedded system because the application is very, very crucial. Both deals with life, one with life of patient and other with the life of our soldiers. So it has to give the results high accuracy and it has to function elegantly and efficiently. And it is very important to make that the design of this embedded system is also very simple. The design of a normal product and the design of embedded system are quite different because, as I said, since it does only very specific tasks, generally the embedded system design will be very simple. The user interface will be very, very simple. The embedded systems also revolves and functions around this tight constraint. You will see what are the different constraints that this embedded system is suffering from. The first is the manufacturing cost. The manufacturing cost, I'll give an example to discuss about the tight constraint and the design cost. Take a mobile is an embedded system and the user wants all the high-end capability into their mobile. And of course, the cost has to be minimum. This is the constraint because nowadays the development in the infrastructure, maybe in small scale as well as in large scale, is very, very huge. That also we seen in the first day lecture. We have seen that the first computer which is used in 1945 is very big and it is cost in millions and billions. Nowadays we can have even a high-end computing system, a laptop in a lakh. That is how the infrastructure has grown in leaps and bounds all this year. And this makes us to talk about IoT now. Unless otherwise, if the infrastructure has not come down in a drastic way, this IoT will not have come up to this level in 21st century. So what I'm trying to say is that the user will, for example, in mobile user trying to expect all kind of feature at a very minimal cost because there are competitors who are able to provide the functionality of a mobile like half pixels of camera and the clarity, the memory capacity, processor capacity, and obviously user will try to expect the same thing from other manufacturer also. So it is the embedded systems are tightly functioning in the constraints of manufacturing, design cost, and it also revolves around the performance constraint. As I said, the accuracy has to be very, very high since it also deploys in the critical applications, and the power used by the embedded system should be very low, and it should be ready to mock at aims out by the functionality and by the way it's work and by the elegancy of the embedded system. It, it's it's quite promising. Market is quite promising. These are the 5 different constraints that this embedded system, with these constraints, it is functioning. In other words, and the new Moore's law actually saves this embedded system from this constraints. So what is the Moore's law? It states that in a simple layman terms, I will just say what is Moore's law. It says that the machine gets faster and its computational facility is keep on improving over the years. As I said a few minutes back, when the years and keep on improving, we have a high computing system with a high processing power, with high memory, and this has facilitated this embedded system to function with all the type constraints which I mentioned in the previous slide. So we're going to talk about the embedded system as well as the real-time system. The embedded system, as I said, embedded system, it's more or less performs like a computer, and the crucial part, the complexity part of the embedded system will be done from the user. And one more thing is that, as I said, the embedded system will do only a specific task. As I said, the difference between the IoT device and the computer in the previous lecture, IoT device are very specific oriented device, whereas computer is a general purpose device. Similarly, the embedded systems are designed to do only a single task. There may be subtasks, but this all subtasks will be combined and they will do only one thing, that is they will achieve for the one common goal. And this embedded system also interact with the environment. It takes input from the environment, and based on the input from the environment, it is able to function. That is one beauty of this embedded system. You need not give an input. User need not give an input to the embedded system like you give to the programs. You can take the input from the environment. It's a good thing that it will sense, it will take the input from the environment. That's all about embedded system. Next, we'll talk about the real-time system. In other words, we call it as RTS. This real-time system, when you talk about the real-time system, we always be very keen on the correctness, or you can say the accuracy of an output that real-time system is going to deliver. Apart from the accuracy, since we are talking about the real-time, it has to deliver the correct result at the correct time. When the results are not produced at the correct time, the real-time system, then it is of no use. So the real-time systems need to be very fast and it has to be very accurate, and it has to produce the result at the right time. When the results are not at the right time, then the real-time system is not going to work out, and it will have so many implications. And the below is a diagram which represents how these embedded systems, the real-time systems, are connected. You can say this embedded system is a superset, and you can say the real-time system is a subset of this embedded system. Some of the examples of the real-time embedded systems are nuclear reactor control, flight control, basically any safety critical system. As why these are coming to picture, as I said, the embedded systems are expected to give the results of high accuracy. Having said this, the real-time embedded system example which are given in the slides are very, very crucial applications, like nuclear reactor. You know how sensitive it is. Any leakage or any damage or any falsification done in the nuclear reactor, then I need not explain the impact of something wrong which has happened in the nuclear reactor. That's why these embedded systems are there, because they give the results very accurately that no error will be there in the nuclear reactor. So all the sensitive applications are there in the real-time embedded examples. And of course, an MP3 player, mobile phone, all can be there as an example of the real-time embedded. And there are also examples for real-time but not embedded. So we can say stock market, because the stock value changes at time. So real-time always depends on the time. So stock trading system is the best example of the real-time. Skype, because we have a live lecture now going on in the Skype. So it varies. Each and every second, the frames of the video will move and the audios also will move. So it depends on the time. And we also have Netflix. Any online application with the live streaming will comes under this category of real-time but not embedded. We also have another category, embedded but not real-time. For example, we want to measure the temperature of a room, then it's embedded system. It's not real-time because it can be measured irrespective of the time, and the temperature of the room can be constant for some time. So, and washing machine, refrigerator are all embedded but not real-time. And we're going to talk about in detail about application specificity. The embedded systems tend to be very application specific. As I said, it performs a single task, a group of tasks to achieve a single common goal. It will not take multiple goals and it will not function. It will take a goal and it will divide that goal into many tasks, and these subtasks are work together to achieve a common goal. And there are some exceptions in this category, like cell phones, because we can do many operations in the cell phone. So the cell phones will form the border, and it forms a borderline on this embedded system boundary. And one more thing I like to point out here is that this, for example, take any laptop. For example, I have a Mac in front of me, and you take any high-end system. It's quad-core, and we have high configuration system, and these systems can be purchased in a few lakhs in the current scenario. Imagine whether we are using the system to the fullest potential. A big question mark. Most of the time we use laptop, high-end laptop probably, only to do the documentation, or to prepare a PPT, or to do some simple programs. Most of the time, 99.99% of the time, we are not using this laptops or the desktops to the fullest potential of the capability. In a very rare case, 0.01%, we may use laptop, and that too not for the productive purpose. The laptop resources will be used, or the desktop resources will be used to the fullest potential only if you do play the video games. Of course, if you do some complex calculation to detect the parameters for launching the rocket, most of the resources will be exploited in the system, the desktop. But then, I'm talking a very normal scenario where the fullest potential of a system will get exploited or utilized only when we play the video game. The remaining 99.99%, we are not even using 0.01% of the system capability. And that's a little thing which you should be worried. And when you talk about the embedded system, see, for example, why I'm talking about this, the processing capacity in the laptop, and I'm talking about the embedded system, is that when you are very keen that what are the tasks that you're going to do before buying a laptop, and if you think that you're going to do only the word Microsoft Office, use only the Microsoft Office and minimum use the internet, then you need not go for high-end system. Rather, you can go for a very mediocre system. You can buy around 20K, and you can will be very happy to do the task with that system. And really, if you want to play a video game and all, instead of spending and putting that on a laptop, you can buy a video game player. The video game player, of course, the video game can be also played with high-end system, but the amount of clarity and quality which you get from the video game player will be much high, and you will not get the same in the high-end laptop too, because the video game player, which is an embedded system, is specifically designed to play the video game. So it is better always to prioritize the list before buying the laptop. And if you really need a high-end system, you're going to work on parallel processing, dynamic programming, then you can go with high-end system. Otherwise, you can buy a laptop very cheap with the lowest configuration, which will satisfy all your priorities. And you can buy the specialized embedded system for whatever things, like playing a video game. You can buy a separate video game player, and that will actually give you a rich experience than you got the experience, than you will get experience of by playing the video game in the laptop. So I say, what I'm trying to say is that the embedded systems are very, very specific to a given task. And since it is very specific, the design is very focused on the application. So if we have a video player, I will not have any extra controls. Like I will have only 4 buttons, which will move up, which will move down, left, right, then jump 2 buttons, left, jump to left, jump to right. And the UI is very simple because it is focusing on only one task. It will be very simple. Next, we are going to talk about the hardware and the software co-design of the embedded system. Hardware and software are often designed together in the embedded system. As I said, because it is designed only for a single application, the hardware and software are designed together. And in general purpose system, it is not so. General purpose system is nothing but a laptop with general purpose system. In general purpose system, the hardware and software are not designed together. Best example is that I may buy a Dell laptop and I can install Microsoft Office in it. I can work on it. With Microsoft Office, it's a separate set of software and does have no connection with the Dell. I can run the Microsoft Office in the Dell laptop. That's why I said the general purpose systems uses hardware and software developed by different companies. Whereas in the embedded system, the company which is developing the hardware, it is the one which also develops the software. The one big concern about when both the hardware and software are developed by the same company, the big concern is that the software has to think and always think whenever whenever the user is coding, he always needs to think about how it will impact the hardware, because both manufacturers are the same. That's a big amount of responsibilities lying on the coder working in the embedded company, that they have to function within the limits of the hardware, because they know what is the hardware capacity and what the hardware can do, and having known that, they have to code in such a way that the software, the written code is working well and giving the desired output with the high accuracy in the software which they have. And one more thing I like to say is that whenever you write a program, even in the lab, for example, you always be focused. You always focus on only getting the correct output. You will not bother to write a very efficient code initially, perhaps in general. The ultimate objective of any programmer is to write a code such that he gets a desired output. If at all he has time, and if at all efficiency of the program is being tested, will not find to the program. To find the factors of a quadratic equation, I can write a code in 10 lines, I can write a code in 20 lines with so many loops, where if it is not required, but I can do it. But unless otherwise efficiency is tested, then user will really bother about the loops and the lines of the code. But initially, users will bother only about the accuracy of an output. Second level, they will bother about the complexity of the code. How much time it takes, how much clock cycle it takes to execute the program, how much of memory is being occupied with the program. These are the constraints. So these embedded software developers will have this constraint because they know that limitations of the hardware. So this programmer in the embedded system really have much constraints for writing the code. They cannot write any lousy codes. Their code has to be always optimized, and it has to use only the limited resources which is there in the embedded system. And of course, we also talked about the designs. It's very simple because it's focusing on a very single task. Next, we are going to discuss about the characteristics of the embedded system. There are about 6 different characteristics. It has a dedicated functionality. As I said, dedicated in the sense, only one task, one goal. So it's a dedicated functionality. It's a real-time operation. We can also use, as I said, I give an example like real-time operating system. Real-time system where we use the embedded system. And the embedded system needs to be of small size, low weight, and it has to use only minimal amount of power for its operation. We cannot demand huge input of power supply to it to do the task. And mostly this embedded system, as I said, it used for safety critical application. Hence, the accuracy of the output of the embedded system should be of high accuracy, and it should function elegantly. It is very, very cost sensitive. These are the main important characteristics of any embedded system. Next, we are going to see in detail about the architecture of an embedded system. When we compare about the embedded system with the real-time system, we have seen that the embedded system can able to sense, can able to take the input from the environment. It's a very good point that we're going to discuss in detail here. That has been portrayed as an architecture in front of you. Now we have 4 components in front of us in the embedded system architecture. The first component is the sensors, and the second component is ADC, nothing but analog to digital converter. The third component is nothing but the brain of the embedded system, which is nothing but the microcontroller. In turn, microcontroller has IP core and FPGA. And the third component is nothing but actuators and DC. in fact, actuators, and fourth component is nothing but actuators and the DCA. This DCA is nothing but digital to analog converter, and actuator is nothing but the output which is received from the microcontroller will be passed to the DCA, and DCA will convert the digital to analog, and the actuators will convey the output to the world. So sensors will receive the data from the world, which is act as an input to the microcontroller. And microcontroller will process the input and will throw an output, and the output will be conveyed through the actuators. This is the overall diagram. We can say it is a three component. You remove this DC, and DCA. This is analog to digital converter and digital to analog converter. Remove this, and there are three components: sensor, microcontroller, and actuators. In a high level, there are only three main components. First, we are going to discuss a detail about on intellectual property core. It's a very important component. It is there inside the microcontroller. Microcontroller has three important parts: as a microcontroller, IP, and FPGA. We will discuss about the microcontroller in detail. It's an intellectual property core, and it's an integrated chip. It's nothing but an integrated chip that performs only one function, and it has to be produced in volumes, and it should be cheap. This microcontroller has to be very, very cheap. We cannot expect high-end cost of microcontroller. It should be very cheap. And it is generally used for having the common task like network controller, Ethernet connection, and audio and video FPGA controller. All these things are performed by this IP core. If you look for the definition of the IP core, an IP core is nothing but IP is nothing but intellectual property core is the block of logic. It's a hub of logic or the data that is used for us to make this FPGA is nothing but field programmable gate array or application specific integrated circuit for a product. You can say it's a hub of logic which is make us to program the microcontroller. In other words, we'll discuss that in detail. You can say it's a hub of logic that is used in making FPGA and ASIE to any product. This IP core is a part of EDA. It's a part of electronic design automation industry trend. Why? Because it mainly works towards the repeated use of the previously designed component. This IP core is essential part of any EDA, electronic design automation, because this IPA enables or facilitate for us to use the previously designed components, previously designed components. If we have a component, and if you want to use that, this IP core is the one which facilitate to use the designed components. It is done sometime back. And this IP core should be entirely portable, that is able to easily insert it to any other vendor technology. If a vendor is going to develop a technology, and this IP core should be easily accommodated inside the vendor's product. That's why I said easily portable in the sense it can be easily fit in of any of the vendor's product, so that the design can be used. We can reuse the design which is there already present. Next component which you're going to discuss is FPGA, which is inside the microcontroller. It's nothing but field programmable gate array. This FPGA are generally a semiconductor device that are based around a matrix of configurable logical blocks. If you see at the bottom of this slide, you can see there are four logical blocks, and they are interconnected. That's why it's a matrix of logical blocks connected, where these logical blocks are connected. That has been given in the picture at the bottom. If you clearly look at it, this FPGA can be programmed. Initially, the FPGA can be bought, and it will be not programmed. A single time you can program and configure this FPGA according to the task for which you're going to use. This FPGA can be reprogrammed to the desired application or functionality required after manufacturing. That's why I said it can be programmed according to the purpose or according to the component in which you're going to incorporate it. And generally, these FPGA are faster than any of the software, and it is slower than application-specific integrated circuits. And this programmable nature is the one which makes this FPGA very popular among the embedded systems, and it is very popular in IoT also, because it facilitates us to program based on our need. That makes this FPGA much popular. Next, we are going to see about microcontroller. So now we have seen IP core, and we have also seen FPGA and microcontroller. These all things forms the central component of architecture of embedded system. This microcontroller, and otherwise it is called the brain of the embedded system. Like the brain of a computer is CPU, the brain of an embedded system is nothing but a microcontroller. And this microcontroller can be compared analogically to mini computers. Okay, so that's why I said microcontrollers can be thought of as tiny computers that are added to any physical object or space, and we can also call it as a brain. They also contain the microcontrollers. They contain one or more computer processors in it. Along with the processors, it can also have a memory, and it will have the input and output peripherals. These all things will be integrated in a single circuit. It will have a process, memory, input, output, peripherals, all will be there in the single integrated circuits. Microcontroller is different from the microprocessor. So you have to understand the nuances of this microcontroller and the microprocessor. These microcontrollers are specifically designed for the embedded application. As I said, the goal of embedded system is to do a very specific task. Then it comes that boils down here. The microcontrollers are specifically designed for the embedded applications, whereas the microprocessor is not designed for the sole purpose of the applications. And microcontrollers has less capability than the standard computer processor, of course, because it is very application specific, whereas this microprocessor is not. This is a small difference between the microcontroller and microprocessor that you should have an idea about. And these microcontrollers can also be programmed. This programmable nature of the microcontroller is being exploited much to the core in IoT. The versatility of the microcontroller is what makes it one of the most powerful in the model design, because it paves way for the user to put the code or put the knowledge of their own inside the microcontroller and able to perform the actions that is decided by the user through the controller. That's the beauty of it. Microcontroller, it's a component, it's an embedded system. Whatever user has is idea, okay, is knowledge that can be incorporated inside the microcontroller, and user can perform all his desired tasks, and it can be made functional with the help of microcontroller. So then user has to write a program, right? That user can write a program in any other language. User can write C, C++, Java, or even Python. This Raspberry Pi supports Python. So the user idea can be injected into the microcontroller through the programs. One of the essential tools that need to be programmed in a microcontroller, it's nothing but IDE. When we want to program inside the microcontroller, definitely we should have an integrated development environment. Otherwise, it will be very tough. When we say this integrated development environment, it is composed of all these things. You should have an editor, you should have a compiler, you should have a debugger. All these things forms this IDE, and it is very, very highly important for you to code on the microcontrollers. And as example, IDEO is the mostly used for programming. This is a sample code that you will be writing inside the microcontroller. Sample code, as I said, and I have segregated into 4 different sections. So the first section is about the commands. That's a coding standard usually follow when the programmer write a code. They will explain who has written the code and what is an objective. So that's introductory commands that describes about the program. For example, this command describe what this program all is done. The second component in this section is that variable declaration. Whatever variable you declare here, it's a global variable, and you can access throughout this program. Second, we have the setup section, which will tell which pin can be pointed as taken as an input and which pin will throw an output. And the fourth component is a loop section. That is where the logic of the user is going to be written. And it's very crucial here. I just written that which ID, which